right, last time you guys looked at kind of more of the skill that you need in order to write a linear function. What we're talking about today is how we can model different situations with linear functions. But we're going to start off by talking about what we call the parameters of a linear function and how they affect the graph. So just quick review, we should really all kind of be good with this. Slope-intercept form of a line. We've talked about why we write that y-intercept first. So that value of b is our y-intercept. We want to kind of think about that being initial value when we talk in a real world context. And then we know that m is our slope. We've also defined that as rate of change. These two values, the y-intercept and the slope, those are the values in your linear function that change. These are what we call the parameters. Of the function. And what that is they determine the specific behavior of the function. So obviously a y-intercept of 5 and a y-intercept of -3, those are going to change the behavior of the graph. That y-intercept tells us where the line crosses the y-axis. If we kind of think in terms of a real world context, I know I'm kind of repeating myself here. This tells us the initial amount or initial value in a situation. The slope of a line tells us information about the steepness of a line. Basically, it tells us how... Hello? Hey. Tharp, yeah. Yeah. Sure, no problem. Mr. Swafford wants to see you. He's like, you don't have a class right now, do you? I'm like, yeah.
Oh, it's because I'm doing the open house thing.
Okay, have fun. Okay, so we could also talk about how slope tells us how fast or slow a line is climbing or falling. We can say the larger the magnitude, the steeper the line, and that kind of takes care of both positive and negative. So with that being said, what I'm going to have you guys do is I'm going to have you guys actually in your groups work through example 1 and 2 that are here on this first page. And then I also want you on the back. Oh, I did a really bang up job of numbering these. This should be number 3. I also want you to look at the first example on the back. Okay? So I'll give you guys a little bit of time, 5-6 minutes, probably be enough. Look at those 3 examples with your group. Go. So you have to like fill it out. Yeah, these are like all the equations like getting them. Because if you take negative 1, is it pretty sure? Or would you actually do the answer would be C. Okay, you were right. That's what it is. I'm still right. Or would it be negative 3?
If it's the same as A, then the slope would be 2, right? So it'd be negative.
It's negative 1. Not the 3. But then that gives you.
No, it'd just be negative 2. It'd just be negative.
This one's not wanting you to select an answer.
This is messed up.
Because it's the same equation as like C. Is that like.
C is horizontal.
So, those we get.
Okay, guys, number 2. Yeah, okay. Number 2 is kind of screwed up. Number 2 is kind of screwed up. Use A, B, C, D as your possible answer choices. How about that? Yeah, that works. A, B, C, and D, one of those are your answers for that question. Sorry about that. That is not how it should be. Okay. Which time T is used?
So if it's 1 over 2, it'd be 1. It'd be 1. Yeah. Yeah.
You're kind of talking to yourself. Yeah. Okay. Are given by the formulas. So what time is it here? Which populations are represented by linear numbers?
Not PD.
Not species, yeah. If one's all of them, it's a species. Great. Just listen in.
which town starts out with peak?
So keep B started off the most.
2 more minutes.
The biggest yeah, it was PC. Yeah.
Are we ready? Okay. All right, Libby, I'm going to come to you guys. Tell me for number 1, the order of these for the largest slope to the smallest. Okay, Okay, G, F, D, A, E. Very good, that is correct. So you start with your steepest line that has a positive slope. Decreasing down here, the one that kind of tricks people is E. What's the slope of line E? 0, which is bigger than your 2 lines with the negative slope. Good. All right, so sorry about number 2. This is not worded correctly at all. So one of these is the equation for line E. Jack, what did you guys say back there?
You said E.
Why?
Because it is negative and it has the greatest slope.
Okay, so it can't be A and B because you're right, it's falling left to right, so it has to have a negative slope. And so you're down to these 2, and you're right, it's steeper than the other one, so it has to be that one. Very good. All right, and then number 3, time, T, in years, population of 4 towns are given by those formulas. Part A, which are represented by linear functions. Spencer, what'd you guys say?
You said PA,
Yep. What kind of function is D, guys? Exponential, good. Okay. Part B, describe in words what each linear model tells you about the town's population. Emily, let's go to you for PA. What, from just this formula, what can you tell me about that town's population? Perfect. The initial population is 20,000. Each year it grows by 160. We can make similar statements for B and C, talking first about the initial population. For B, we're decreasing the population by 300 a year. C, increasing by 650. Good. Of those towns that grow linearly, so those first 3, which starts out with the most people, Ben?
I said C.
You not quite. So just not quite. So in these 3, okay, tell me for town A, what's the initial population? Okay, what about B and C? Okay, so which starts out with the most people? Okay, but that's what happens like each year. This is just asking you what at the initial when t is 0. Okay, we're looking for that initial value being the greatest. And then which is growing the fastest? Zach, what'd you guys say? Good. C. Okay. All right. Sounds pretty good. Grab your calculators because we're going to use them a little bit here in this next part. Looking at the intersection of two lines. The ordered pair XY, where two lines intersect, is going to be an ordered pair that satisfies the equations for both lines. To find that point, you guys have been doing this for several years, we're going to solve those equations basically as a system. When modeling, a real situation, the point of intersection often has a practical meaning, okay? So in this example, we are given the population of two different countries, where population is in millions. It says, in what year will the populations be the same? So let's start there. So if I'm looking for when these populations will be the same, algebraically, we can set them equal to each other. So then let's subtract our 2.2, subtract the 25. And we get our value of t as 20. We need to keep working on not just stopping there. Okay? You guys know how to solve an equation. What we're doing here is now understanding what that value means. Okay? Robert, what does that 20 mean? In 20 years, the populations are the same. Very good. All right, I also want to show you how to find on your calculator an intersection point. Go ahead and go to your y equals and just plug in both of those equations. And then hit zoom 0, which is your zoom fit, and you should be seeing what I have up here. So zoom fit, it's showing us both of those lines, but it's not showing us what we're concerned with, which is what? Where they intersect. So what we need to do is we still need to go back to our window and increase. Let's try just increasing. I didn't write down what it should be, so I don't even know. Let's increase our X max to start off with, see if that works. I don't know, maybe 50? Now what do I need to change? Yeah. Sometimes it's really just kind of a game of playing around until you get what you want on your calculator, which now we have what we're looking for. Now, do this with me. If you hit second trace, it says calc right above there. So hit second calc. And this is an option that we're going to use quite often throughout the course. There's a lot of things here that are helpful. Number 5 is intersect. So go down to option 5, hit enter, and then it's going to ask you 3 questions, okay? It wants a point, and you might have to move your little spider using your cursor buttons. Move it away from the point of intersection a little bit. It wants a point on your first curve. Hit enter. It wants a point now on your second curve. Hit enter again. And then it's asking you to guess. So the best that you can, move your spider. I call that little cursor a spider. I don't know why. It looks like a little spider crawling around. Move it kind of on top of that point of intersection, hit enter again, and then it will tell you exactly the coordinates of where those intersect. Now, obviously, we solved it algebraically first, so we already knew that x value was 20. But what we didn't know was that y value. So what does that 109 mean? What does that 109 represent? Okay, but in our context, in what we're talking about. That's it. So that y is representing our population. So that 109 means in 20 years, both populations will be 109 million. Awesome. Okay. Next question here. In what year will the population of country A double the population of country B? So we just need to set this up so that we're showing that country A is equal to double country B. So 65 plus 2.2t. So country A is double country B. What I want you guys to do, just to kind of practice a little bit, using your calculators, go ahead and solve this algebraically. And then kind of like we did with the first part, I want you to graph both of these. And then I want you to work with your calculator, make sure that you're able to get that intersection point. Okay, go.
Just get rid of the 2 on the other side.
Well, then go to your window and I did -200 cubes.
I didn't test it. Like, I didn't even try, I guess. I just don't
Yeah.
Okay, go back to blank. Okay. Then let's first of all go back to Zoom 6. How to reset our window. Okay, now hit Zoom 0. See it. Sometimes you kind of have to like reset it. Oh, you know what? You have that one turned off. That's why. So you have your equal sign wasn't dark. There we go. Shit, crap it now. Oh, gosh, I've seen this before. Since I know you're the other. I'm gonna do it later. I have to look it up. Because see how you have those weird symbols over there? I forget how to fix it. I'll look it up, but I have that issue. Can you wait till we're done with the lesson? Okay. Yeah. Okay, I'll have to work with you guys later. I gotta go. I gotta move on. Okay.
All right, guys, we're gonna finish this up. Algebraically, we should be getting 2.42. If you were able to get that on your calculator as well, that's great. We'll have time later. I can get with you one-on-one, but I can't spend, all of class time doing calculator stuff because sometimes that happens. All right, last thing, talking about inequalities a little bit. Just kind of some basic stuff here. Some situations are better modeled by an inequality rather than an equation. So the example that we have is that a dog requires 1,300 calories per day. A cup of dry dog food has 350 calories. The dog has already eaten a can of wet food containing 400 calories. So set up a linear inequality to model this situation. So basically, the number of calories that this dog has already consumed. So I'm looking for basically how many cups of dry dog food. So 350 calories for every can N. And that amount needs to be less than or equal to 1,300 calories because the dog can eat up to that amount. And then part B is basically just asking you to find that value of N before the dog would exceed its caloric limit. Okay, so you guys could finish solving that algebraically for N.